Okay, let's continue the discussion about power series. In the study of the power series, we have the absolute convergence. We also have the uniform convergence. Let's first discuss some property about uniform convergence. So, lemma 3. Let Fn be a sequence of a continuous function. Sequence of continuous functions on a set S, arbitrary set S in a complex plane, and converging uniformly to F on this S. Converging uniformly on this S. Then F is also continuous on S. So in the short sentence, it just means the limit of uniform convergence of continuous function is continuous. So the continuity is preserved by the uniform convergence. And we do have an example which show that the continuity is not preserved by the simple convergence. The convergent limit of continuous functions may not be continuous. Okay, if you only have the convergence, not uniform convergence, a sequence of continuous function may not give you the continuous function. Okay, so that's the state claim. Now let's see how we use the uniform convergence to prove the continuity of the limit. Okay, to show the limit function is continuous at a point. Limit function is continuous at z0 in this set S. So we're going to have a epsilon and a delta, right? So for any epsilon greater than 0, there is a delta greater than 0 such that for any z in S, with distance between z and z0 is less than delta, we have ops value f of z minus f of z0 is less than delta epsilon, less than epsilon. Okay, so this is a definition of a continuity. Okay. Okay, so we want f of z minus f of z0 is less than epsilon. But what we do is the following: f of z is the limit of fn of z. So there is a capital N such that it's a uniform continuous convergence, uniform convergence. So there is a capital N such that for all z in the S set S, f of z, fn of z, this distance is always less than epsilon over 3. So we want the answer is better, so we divide it by 3. Okay? So first of all, for arbitrary z, here this z is different from this z. Let's use w instead of z. Let's use w. Okay? So for all w in S, fw minus fnw is less than epsilon over 3. This is uniform convergence, always very, very close to it. And second, you pick up this fn. For this fn is continuous at z0. Fn is continuous at z0. For epsilon over 3, there is a delta greater than 0, such that for z in S with z minus z0 less than delta, fn of z minus fn of z0 is less than epsilon over 3. It's less than epsilon over 3. Okay? So now what we have, we are going to combine these two stuff. Okay, so how do we combine? For z minus z0 is less than delta, we're looking for f of z minus f of z0. We're going to apply our famous trick. We insert fn of z and we'll insert fn of z0. So see here, this is a minus plus, this is a minus plus. We don't change the opposite value, so it's still the equality at this step. And then we group them, see. We group them. We apply the triangle inequality. Right? And here, the first term and the third term, we use the uniform convergence property. For the same point, fn, f, they are very close, so it is less than epsilon over 3. Here it's less than epsilon over 3. This is uniform convergence. The middle term, it comes from the continuity of this fn. Only the middle term give us the delta, or use the middle term uses the assumption of a delta. And the first and the tail, first and the last term, they only use the uniform convergence. right? And then this is a less than epsilon. Epsilon 3, epsilon 3, epsilon 3 is epsilon. So we finish the proof. So we want to show the continuity of f. We basically pass it to some closed function, fn. Fn is continuous, so you get the continuity. And you can do that because you have this n independent of the point z and z0. If this n depend on this point, then you cannot do it. You cannot do it, right? Yeah. So that is the proof. So the uniform convergent limit of a continuous functions is continuous. Okay, so with this theorem in mind, we prove the theorem 8, the lemma 3 and the theorem 8. Theorem 8 says let fn be a sequence of continuous functions on some set, on a set S. And this S containing in a contour gamma, and contour gamma. And suppose that Fn converges uniformly to F on S, then the sequence. What sequence? So this part we get the continuity of F. And second, when you have a continuous function, you have a contour, you can do the integral. So the sequence, you integrate each Fn along gamma, you get a number. You have a sequence of complex number. This sequence of